Hello students, welcome to the last class of the Thermodynamics. This is your tutor Pragya Sahu, PMRF Chemistry, IT Kanpur. Okay, so in last class we were studying Gibbs free energy. Okay, then we studied the relationship between your Gibbs free energy, your enthalpy change and the entropy. Okay, after that we studied the spontaneity and randomness. Okay, that is delta S entropy of the system. Okay, and then after that we studied the changes in entropy, like entropy of vaporization, entropy of fusion, entropy of transition, etc. Okay, so let us start with the Gibbs free energy work done. So for any system at constant pressure and temperature, what is the value of delta G? So delta Z is delta G, your delta Z is your delta H minus the delta S. And we know that your delta H is equal to delta U plus P delta V. That was the relationship between your enthalpy change and the internal energy change. Okay? That is delta U plus P delta V. So if you substitute the value of delta H in the equation where your delta G is equal to delta H minus T delta S, this will become delta Z equal to delta H. Delta G is equal to delta H minus T delta, and we know that your delta H is equal to delta U plus P delta V. Let us say this is equation 1 and this is your equation 2. If we substitute the value of delta H in your equation 1, the value of delta H in equation 1, what will you get? You will get delta Z is equal to delta U in place of your delta H, and minus T delta S will be as it is, minus of T delta S. And we know that from first law of thermodynamics, your delta U is equal to the summation of heat and work done, that is Q plus W. From first law of thermodynamics, right? From your first law of thermodynamics, your delta U is equal to Q plus W. And if you substitute this value, and from 6, what does it say? Your delta S is equal to Q by T. Okay? And from 6, law of thermodynamics, your delta S is equal to Q by T. Let us substitute the value of delta S and delta U in this equation 3. Okay? What will you get? Your delta G will become delta U will become Q plus W plus P delta V and minus T into delta S at the place of delta Q by T. Now let us solve this. This T and this T will get cancelled out. You will get Q plus W plus P delta V minus of Q, and this plus Q and minus Q will be cancelled out. And what will you get? You will get your delta G will become W plus P delta V. So your delta G will become W plus P del V. If you multiply both the sides with minus, what will you get? Minus of delta G equal minus of W and minus of P delta V. And minus P delta V represents the work done due to the expansion, and this expansion is again against a constant external pressure. We know that your minus P delta V means this term represents the work done due to expansion against a constant external pressure. And from here, it is clear that the Gibbs free energy, that is minus of delta G, is accompanying a process taking place at a constant temperature and pressure, is equal to the maximum work obtainable from the system. Okay? So what it says that It is clear that in free energy accompanying process, that means a process which by the company of gives free energy at a constant that is equal to the maximum work obtainable from the system other than the work of expenditure. Okay. So therefore, it is clear that the free energy, that is the decrease in the free energy accompanying a process taking place at constant temperature and pressure is equal to the maximum work obtainable. This is equal to the maximum work which you can obtainable from the system other than the work of expansion. Okay, other than the work of expansion. Okay, so this is what is the chemistry energy and the network journey. Okay, now let us study the criteria for the spontaneity of a process. So, what is the process for the what is the criteria for a process to be spontaneous? So, the spontaneity of any process depends on three different factors. Then, the first one is the if the enthalpy change of a process is negative, then the process is exothermic and may be spontaneous. Okay, so this is what we have studied in that case. The reaction was exothermic and the process was spontaneous. So this is the same thing where if it's enthalpy change of a process, then the process is exothermic and it may be spontaneous. That is your delta H is negative. Next is if the entropy change of a process is positive, like if a process is happening with where your entropy is increasing, like that means your entropy change is positive, entropy change of that process will be positive, then the process may occur spontaneously. Okay, so if we can say that this process is spontaneous. Next one is if the gift free energy, which is the combination of both your delta S and delta H, what that is your delta G is equal to delta H minus delta S, so it is a combination of both, then it should be negative for a spontaneously. So this means if a reaction occurs spontaneously, that means the delta G value of that reaction will be negative. And that is the necessary condition for a reaction to be spontaneous. Okay, that means your delta G should be less than 0. That means it should value should be a negative value. And your delta G, if your delta G is less than 0, that means your delta G is equal to delta H minus delta S. Your delta G should be less than 0 for a reaction to be spontaneous. If that is the case, your delta G is equal to delta H minus delta S. This should also be less than 0. Okay. This your delta H should be less than delta S. So this is the case. And this is the condition. This is the necessary condition for a reaction to be spontaneous. Okay, so I will write the third condition over here. That is the Gibbs free energy, which is the Gibbs free energy, which is the combination of the above two. Combination of the above two, that is delta H and delta S, should be negative. Should be negative for a reaction to occur spontaneously. For a reaction to occur spontaneous. Okay, that is your delta G should be less than 0. That means your delta H minus T delta S should be less than 0. So this is what the of a process. So this is a table showing the effect of temperature on the spontaneity of the reaction. Okay. So if your delta H is negative and is positive, what will happen? Your S is positive and your delta H is negative. Your delta G is equal to delta H minus T delta H is negative. That means this will have a negative value. Let's say it is minus X. Okay. Let's say the value is minus X. And it is say your delta S is positive, will be positive, and plus minus will become minus. And if you solve this, okay, so minus minus will become plus, and we will get a minus sign. That means your delta G will be negative here. Okay, that means your delta G will be a negative value here because this is minus and this is minus. These both are having a negative value and they will add up and give a minus sign. So in turn, your delta G will be having a negative value. That means the process, that means it is less than zero. That means process will be spontaneous. Okay, that is spontaneous. So whether the temperature is low or high, whatever the case, the process will be spontaneous at all temperatures. Okay, so here it is written that the spontaneous at all temperatures. Okay, so for example, this one, the delta H of this reaction is negative, and your delta S that is having a positive value because here your entropy is increasing. Here entropy will be what value? Entropic change is 3 minus 2, that is 1, which is a positive value. That means your delta S is having a positive value, and the enthalpy change of this reaction is negative. Okay, so this is how it makes. Next, what if your enthalpy of reaction is negative? Enthalpy change of the reaction is negative, but and your entropy change of the reaction is negative. Right. So if negative, then this term will become positive. Okay, so this will become a positive. So here we will have in second case, let us say this was the first case, right, and this is second case. In second case, what will happen? Your delta G is equal to your enthalpy change of the reaction is negative, that means minus X, and your T delta S. Now your delta S is also negative, so it will become a positive sign. In minus minus will become plus. So in this case, if your T delta S, what? Let's say if your temperature is high, okay. So if temperature is high, that means this value will be greater than this value. So if this value like means your T delta S is greater. So in last slide, I have told you that your delta H should be less than T delta S. So in this case, here your T delta S is greater than your delta H value. Okay. So if T delta S is greater than your delta S, then what will happen? This will be high value. That means your delta G will be having a positive value. If that is the case, if your delta G is having a positive value, then that means your reaction will be a non-spontaneous. So at high temperatures, the process will be non-spontaneous. So it is at high temperature, the process will be non-spontaneous because in this case, your delta G will be greater than 0. And at low temperature, what will happen? If this one small, that means your T delta S value is less than your delta H value, then in that case, what will happen? Your delta G will be less than 0 because here minus part is having a higher value. So that's then 0. So the process will be lower. Okay, so this one shows that at low temperature, the process will be spontaneous if your delta S both are okay. For example, this is adsorption of gases follows these things. Okay. So what if your delta H and your delta S both are positive? So here, if your delta H is positive, that means plus of x minus k delta x is also positive. So if this is having a positive value, okay. So if your T delta S is less than your delta H, okay, so plus H. So at low temperature, your T delta S will be less than delta H. In that case, your delta G will be positive. That means greater than 0. If that is the case, the process will be non-spontaneous. Okay, so that means at low temperature, one second. So at low temperature, what will happen? Yeah. So if this is low, that means your T delta S will delta H. Okay? That means your delta H will be greater than T delta S. And if you subtract this, you will get a positive value. That means your delta G will be greater than 0 and the process will be non-spontaneous. And at high temperature, okay, and at high temperature, if temperature is high, that means this value will be T delta S will be greater than your delta H. If that is the case, the whole value will delta G will be less than 0 and this will make the process spontaneous. So it is written that at high temperature, the process is spontaneous if your delta H and delta S both are positive. And the example is thought. Okay. So let us move to the last class where it is. What if your delta H is positive and delta S is negative? So if I will write here, if delta G, your delta H is positive, that means plus of X, and delta S is minus minus, it will become plus, and the whole value will become T delta S with plus sign. So here both are plus, that means your delta G will be greater than 0, whether the temperature is low or high. So if that is the case, so your process will be non-spontaneous always. Okay? So that at all times spontaneous if your delta H is positive and delta H is negative. Right. Okay, let us move to the next slide and derive the relationship between your delta G naught, and that is standard free energy change, and equilibrium first. Before that, okay, so I had there was a problem, but we will solve that problem in last. Okay, let us first derive the relationship between your delta Z naught, that is standard free energy change, and your equilibrium. So it is in perfect equilibrium with its surrounding at all times. Okay, in reversible process, the system is in perfect equilibrium with your surrounding at all times. Your system is in equilibrium with your surrounding at all times. A reversible reaction, a reversible chemical reaction can proceed in either direction simultaneously. Okay, both reaction can happen. So that a dynamic equilibrium, there will be the equilibrium. Okay, so this means that the reaction in both the directions decrease in the free energy. Okay, so if the reaction is happening in both the directions, that means decrease in free energy, which is impossible. So it is possible only if at equilibrium the free energy of a system is minimum. Let us consider a general equilibrium reaction, that is A plus B is giving C plus D, and this is equilibrium. Okay. So the free energy change of the above reaction in any state, that is delta G, is related to the standard free energy change of the reaction according to the following equation. And that equation is your delta G is equal to delta G naught, that is the standard gas free energy change, plus RT ln Q, where Q is your quotient of the reaction. Q is quotient of the reaction, and it is defined as the ratio of concentration of products to the concentration of reactants. Concentration of product divided by the concentration of your reactant. Okay, under non-equilibrium condition. Okay, so this is the relationship between your reaction and the standard gas free energy change. Okay, Now, when equilibrium is attained, there is no further free energy change. That is, your delta G will be equal to zero at that time, and your Q becomes equal to the equilibrium constant at that in that condition, because the concentration of will be equal in the equilibrium condition. Okay, so your delta, your Q will become K equilibrium. So in that case, the above equation will become, so when equilibrium is attained, there is no further free energy change, no further free energy change. That means your delta G is equal to zero. If that is the case, your delta G is equal to delta G naught plus RT ln Q. Here, your delta G is equal to zero. That means plus delta G naught plus RT ln. Here, your Q will become K equilibrium. That is your equilibrium constant. Okay, K equilibrium is your equilibrium constant. So if you solve this, you will get delta G naught is equal to minus of RT ln K equilibrium. Okay. So this equation is known as the Van-Hoff equation. So this equation is also known as Van-Hoff equation. Is known as Van-Hoff equation. And if you solve this, it will become minus of 2.303 RT log, because here it is ln. If you change it into log, your 2.303 will become K equilibrium. And we also know that your delta G naught is equal to delta H naught minus T delta S naught. So if this is the case, then that means this implies that your delta H naught minus T delta S naught will also be equal to minus 2.303 RT log of K equilibrium. Okay, so just remember these equations. Okay. What? Now let us move to the third law. Now we have understood what was the first. Then we studied the second law of thermodynamics and the statements there. Let us now study what the third law of thermodynamics. So the entropy of a substance, where I have increased the temperature, your will increase. Like here, from this relation, you can say that your entropy of a substance varies directly with the entropy is directly related with the temperature. So lower the temperature, lower is the entropy. Okay. For example, let us say water above 100 degrees Celsius at 1 atmospheric pressure exists as a gas. Okay. So water above 100 degrees Celsius exists as a gas and has a higher entropy, because I've told you that water in solid, water in liquid, and water in gaseous state. Okay. So in your gaseous state, this was having a higher randomness. That means the delta S was positive. That means it was having a higher disorder. Okay, so the water molecules are free to roam about. So let us say in this example. Okay. So because the water molecules in there are free to roam about in the entire container, because they are in gaseous phase. So when the system is cool, when you cool the system, the water vapor condenses to form a liquid. Okay, so now the water are in your gaseous phase. Now you can form a liquid. So what will happen? The water molecules in liquid phase can move about somewhat freely, because now they will not have more space to move. Okay, so now they can move only in the only very less. Okay, there will be only very less movement. Okay, thus the entropy of the system has decreased. You are going from to liquid state. Okay, so what will happen here? You become because of the condensation, now your liquid cannot move more freely. So here your delta S is decreasing. That means from here to here, your delta S is less than zero. That means your entropy is decreasing. So on further cooling, water freezes to form ice crystal. That means if you go from here to here, it will form ice crystals. And the water molecules in the ice crystal, we know that they are highly ordered and the entropy of the system. Okay. So they are in highly ordered manner. So if we cool the solid crystal still further, the vibration of in the crystal lattice gets slower. So what is happening? So here the molecules that are held in the crystals, there will be very less vibration. That so and they have a very less because they will not be very free to move over there because of slow vibrations. Okay, so they have very little freedom of movement over there. That means little movement. That means there will be very okay. So there will be very little disorder, and hence your entropy will be very small. Hence very small. Okay. Right. So on going from gaseous state to liquid to solid, your entropy is basically decreasing. So at absolute zero, that is at 0 Kelvin, that is minus or 0 degrees. Okay, so at absolute zero, that is your 0 Kelvin, theoretically all modes of motion is stopped. So there is very less vibration, or we can say negligible vibration. So all of the motion is stopped absolute zero, that an object can get arbitrarily close to what absolutely zero will remain unattainable. Okay. Thus, the third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero is zero because all modes of the motion stop here at that temperature. So, thus, the third law of thermodynamics states that the third law of thermodynamics states that the entropy of pure crystalline substance substance is zero at absolute zero. Is zero at absolute zero temperature. Okay, that is 0 Kelvin. Otherwise, it can be stated as it is impossible to lower the temperature of an object to absolute zero in a finite number of steps. Otherwise, it can be stated as otherwise it can be stated as it is impossible to lower the temperature of an object. It is impossible to lower the temperature of an object to absolute zero in finite number of steps. Absolute zero in finite number of steps. So mathematically, it is shown as limit t tends to zero s tends to zero. Okay, for a perfectly ordered crystalline state. For a perfectly ordered crystalline state, your S is equal to zero, that is entropy is zero when your T tends to 0 Kelvin. Crystals with defects, that is imperfect zero, have entropy greater than zero, okay, because they have the that means defects. So in that case, your absolute entropy of a substance can never be taken. Okay, so the crystal with defects or imperfection at absolute zero have that entropy greater than zero, your S is greater than zero, and your absolute entropy of a substance can never be negative. Clear? Entropy of a substance can never be negative because there will always be the randomness, imperfection in the system. Okay. So this is shown over here that at 0 Kelvin, your entropy is zero, that is at absolute two. And if we increase the temperature that is greater than 0 Kelvin, there will be the randomness in the system and your entropy will increase. So when you increase the temperature, your entropy will increase. That means your S will be always having a positive value. Your entropy will have a positive value and it can never be a negative. Now let us solve some problems. Here it is given that calculate delta G naught for conversion of oxygen to ozone at 298 Kelvin if your Kp for this conversion is 2.47 into 10 to the power minus 29 units. So your delta, you know that delta G naught, that is standard free energy change, is equal to minus 2.303 RT log Kp. Okay. So we know R here, we know temperature is here, that is 298 Kelvin. Kp is also given, that is 2.47 into 10 to the power minus 29. Now we have to calculate this value of delta G. So you're equal to minus of 2.303. R is having, the value of R is 8.314. Your Kp, your temperature is 298 Kelvin. And then we will take the log of 2.47 into 10 to the power minus 29. Okay. So if you solve this, you will get the delta G not equal to 16,300 joule per mole. If you change this joule to kilojoule, it will become 16.3 kilojoule per mole. Okay, so we were asked here standard gives free energy for the conversion of oxygen to helium, which is P by 2 of O2. This is an equilibrium reaction. Giving O3 gas. Okay. And this is happening at 298 Kelvin. So Kp of this reaction was given to us. Okay, so for equilibrium, we know that your delta G naught is equal to minus 2.303 RT ln K equilibrium. So here Kp is given, so we put Kp over here and we substitute all the values given in the question. So now let us, which is calculate the entropy change during the melting of 1 mole of ice into water at 0 degrees Celsius and 1 atmospheric pressure. In that, enthalpy of fusion of ice is 6008 joule per mole. So now we have to calculate the entropy change here. So what is the melting of ice into water is basically fusion. So ice to water is fusion. Sorry. To water. This is your fusion. And your delta H of fusion is given, that enthalpy change of fusion is given, and that is 6008. Okay. Now we have to calculate delta S fusion, that is entropy change during the reaction. This we have to calculate. We know that here water, which is in solid state, is getting converted into liquid state at 273 Kelvin. Okay, so I'll just drop this. Now let us just calculate the delta S rate. Your delta S of fusion in this case will be equal to delta H of fusion by T. And your delta H fusion is given 6008 joule per mole and temperature is your 0 degrees Celsius. So T is your 0 degrees Celsius. If you convert, it will become 0 plus 273, that is 273 Kelvin. Your temperature is 273 Kelvin. So if you solve this, it will become your delta S fusion will be 22.1 0.007 joule per Kelvin per. Okay, so this will be the value of your entropy change during the reaction. Now let us solve the next question, which is 2 mole of an ideal gas is expanded reversibly and isothermally from 1 liter to 10 liters Celsius. Find out the free energy change in calories. So we have to calculate the delta G in calories over here in this portion. So we know that for an H is 0. If your delta H is 0, you know that here your delta H will be equal to 0. So if your delta H is equal to 0, your delta H is equal to 0, that means we know that delta G is equal to delta H minus of delta S. So if we substitute the value of delta H 0 over there, we will get delta G is equal to 0 minus delta S. So your delta G will become, with delta G is equal to minus T delta S. Okay, so we know that. And if we substitute G as delta H is equal to 0 over here, you will get delta G is equal to minus of T delta S. So now we have to calculate the entropy change because we know that we don't know the value of delta S. In order to calculate delta S, we have the formula that your delta S is equal to 2.303 NR ln V2 by V1. Okay, so this is the formula for delta S. So if you substitute this value over here, you will get your delta G is equal to minus of 4.303 n into log of V2 by V1. Okay, so if you know the value of N1 here, that is 2 mole, and 2 mole is given n equal to 2 mole. V1 initial volume was 1 liter, and final volume, that is V2, was 10 liter. So we know the value of V2 and V1 also. So let us just substitute the values in this equation. If substituting the values of N, T, V2 and V1 in the equation, let us say 1, we will get delta Z equal to minus 2.303. N is your 2. And we are asked to calculate it in calories. So in calories, your R has a value of 2. So R will be 2. Temperature is given 127 degrees Celsius. So if you convert this, you will get, in Kelvin, you will get 400 Kelvin. So your temperature is 400 Kelvin into log of V2 is your 10 and V1 is your 1. So if you solve this, you will get minus of 2.303 to 1600, which is equal to minus of 3683.8. So your delta G, that is the free energy change for this reaction in calories, is minus 3680.8 calories. Okay, so now let us move to the next question, that is, at 1 atmospheric pressure, your rate of vaporization is 4.3 kilojoule per mole and entropy changes per Kelvin per mole. Then we have to find out the equilibrium temperature. So we know that at equilibrium, we know that your delta G is 0. Your delta Z is equal to 0. And if your delta G is equal to 0, we know that delta G is equal to delta H minus T delta S. And if this is 0, this will become. Okay, so now if you solve this, you will get delta G equal to T delta X, and we have to find temperature. So it will become T will become equal to delta H. Delta H is given, that is the heat of vaporization of water is 44.3. So delta H is 44.3 kilojoule per mole. And your delta S, that is your entropy change, is given 120 joule per mole. So if you solve this, substitute this value of delta H and delta S over here, you will get delta H is your 44.3 kilojoule. That is in joule divided by 120 joule Kelvin joule per Kelvin per mole. Okay, so joule per Kelvin per mole. So if you solve this, your per mole will get cancelled out, joule will get cancelled, and this Kelvin will go above and will become Kelvin inverse will go above and it become Kelvin. So that is 369 Kelvin. Okay. So this is the equilibrium condition, which is 369 Kelvin. So, in conclusion, in this thermodynamics course, we started firstly with the basics like what is your system, what is surroundings. Okay, then we studied the what are extensive, what are intensive properties, read about that, the whether it is an extensive or extensive property. So after that, what we studied about the state function. We studied what a state function, what a path function. They are the state function that are the thermodynamic quantity that depends only on the initial and final state of the system, and path functions where the properties that depends on the path. Like for example, your pressure, volume, and temperature state functions, and your heat, work, or energy due to any kind of energy that were the path functions. Okay. So after that, energy, what is internal energy? So internal energy was the energy associated with the conditions of temperature and pressure. And so it was a change occurring during the process at constant temperature and constant volume. And after that, the system at a particular temperature and pressure, and we can also call a system. And after that, the relationship between the internal energy, that is equal to U plus PV. After that, we studied the first law of the law of conservation of energies, like the first law of thermodynamics, where that which states that the energy of the universe always remains. And mathematically, we got the equation that is your delta U was equal to Q plus W. Okay, and after that we studied various kind of work, that is work of expansion, compression, reversible and irreversible processes. After that, we started studying the entropy, um, entropy change, the spontaneity and randomness that we studied in the last class. Then into the class, we studied its free energy, the relation, and we solved some problems. Okay, so this was all for this thermodynamic course. Okay, so I'm ending this session for now. So if you have any doubt, you can reach me out. Okay. So I'm ending this class.